Welcome to this video. In here we're going to talk about tester interval for LSRL. Take a look at this example. A developer at a tortilla chip company is curious about the relationship between how long the chip has been deep fried and the amount of moisture in the chip. He collected the following data right here. If we want to graph it into our calculator, we will first enter all of this data in and graph a LSRL. You may be familiar with this word, LSRL. We've introduced that in Unit 2, and now we revisit it in Unit 8. From this graph, you can see there is a strong negative decreasing relationship between the frying time and the moisture content. So here's a couple characteristics. It's negative, it's moderate. You can argue both ways. In my first look, it seems strong to me. And it's nonlinear. And if we want to graph it using a residual plot, it will be, we want completely randomness, like no pattern, no fan shape. But in this class, we're going to introduce a new type of graph, which has x-axis as beta and y-axis as the residual. So what's this graph means? Well, let's take a look. So first of all, as always, we will set up our 4 steps. What's beta? Beta is the true slope of the LSRL between frying time and moisture content. So before we, like in the previous videos, we've been talking about mu or p proportions or means, but in here we're talking about beta, which stands for the slope. And the null hypothesis will be the beta is equal to 0. An alternative hypothesis will be beta not equal to 0. You can also write it in less than, greater than, or not equal to, depends on the question. But because in this question we only want to find is there a relationship or not, the question didn't specifically set which direction. So we would just say not equal to. Second step will be stating the name of the procedure, which in this case will be t-test for the slope of LSRL. We will draw 2 graphs, the residual plot and residual box plot or histogram. You may be familiar with residual plot, but what's residual box plot or histogram? Let me talk with you going deep, because that's another way to express your data and help reader to visualize what's going on. The degrees of freedom in this case will be n-2. N is 8 because we have 8 different time recording. That's 8 different categories. -2 gives us 6, so that's our degrees of freedom. Let's first draw our old stuff, which is the residual plot. Go into your calculator, and after entering all of those in, you'll get a dot plot like this, which you can see that there's roughly equal number of positive or negative residuals. There's no fin shape, and there is a pattern, unluckily. Because in here we can say that it seems like concave up. It's like a quadratic function or something. And in order to let the residual plot completely useful or completely effective, we want it to be as random as possible. So don't forget to label y and x axes, but because there's a pattern, so we have to be note of it. And let's take a look at residual box plot. What's that? Well, you're gonna go into your calculator and hit box plot, but instead of using L1 and L2, you're gonna use resid for your x list and leave frequency as number 1. And then you will get a graph like this. What's the characteristics of it? There's no outliers, but it shows skewness. It kind of skewed right for us. Therefore, since residual plot and residual box plot both have some conditions didn't match our requirements, our t-model is questionable. We will draw this statement again in our conclusion later. Let's take a look at step 3. Step 3 basically showing graphs, formulas, and some key terms. So it seems like a lot, but after we break down, it's not that bad. First of all, t. We're going to use the formula b minus 0 over se sub b. What are those letters mean? Well, for the letter b, that's the number that when you graph your LSRL curve in your calculator, when you hit LSRL, and you will get a bunch of like numbers, like you will get a linear equation, and down there it shows r squared, a and b, etc. So from that you will find your b value. And what's the 0? It technically it's not 0, but for our case it is because our null hypothesis is 0. So it really depends on your question. If your question's null hypothesis is beta equal to some number, then in this formula right here, you're going to write this number down, not 0. SE sub b stands for the standard deviation of sampling distribution of slopes. So remember that beta, the definition for it is the true slope of LSRL. So SE sub b is basically the after we collecting a bunch of slopes from a lot of samples, we create a sampling distribution just as we did sampling distribution for means and proportions in previous lessons. And here we're doing the slopes. So you can see a bunch of lowercase b made up our normal curve. So that's what SE sub b stands for. You will use this formula, but what's this t? Like, where did you get this t value? Well, you're also going to go into your calculator, and you're going to hit stat if you're using a TI-84. Go into tests, and scrolling all the way down until you see linear regression t-test. From there, you will enter xlist as L1, ylist as L2, frequency leave it as 1. For the beta, or like that weird letter, we don't really care about that. Just know that it's the same meaning as beta. And hit like not equal to 0, and set regression equation, leave it as y1. If you don't know how to hit y1, just hit alpha, trace, and then number 1. From there you will get L1. And then you got a bunch of numbers. That's basically all you need for step 3. You're just going to copy them down. So that's how I got t for this question. You're going to also label p is equal to what, and se sub b is equal to what. What's s? So se sub b, we're using a formula, right? So we arranged the first formula a little bit, make it b over t, and b we already know from the step that we are using our calculator to do the LSRL for the original data. We already get that value, and we got t from here. We just divide those numbers up, and we will get 0.067. So that's it's not a coincidence that two negative numbers after dividing up, it gives us a positive number. In reality, that standard deviation will always be positive because it really stands for a range or a length on the curve. So it cannot be negative, right? Because length cannot be negative. Therefore, it's reasonable. If you got a negative standard deviation, you might be thinking about yourself, am I really doing the right thing? And degrees of freedom will be 6. That's how we got from n minus 2, which is 8 minus 2 gives us 6. And it's always not a bad thing to rewrite the equation again, just showing that you have full picture, all of the information's down. Then comes to the drawing stuff. We will use the standard normal curve, label the 0, like the beta null hypothesis in the middle, the peak of the curve, and label the b values on two sides, both sides, because we are testing for two-tailed. In this case, we're saying it's not equal to 0, therefore two-tailed. Don't forget to label SE sub b, 0.067. I just realized that I forgot a 0 in here, so make sure you write it for yourself. And that's just little informations about the meaning of these letters. SE sub B is the standard deviation of sampling distribution of slopes. S is the standard deviation of the residuals that we got. So both of them are standard deviations, but you can see that they are very different. First of all, SE sub B, just as we said, it's you collect a bunch of samples, measures their slopes, and put them in a sampling distribution, and you will get the standard deviation of that sampling distribution created by summing up all of the slopes you collected from different samples. While S, on the other hand, is the standard deviation of the residuals from our data right here. So you can see we don't have all the data. So it's the residuals from our sample data, actually, to be accurate. But it's also the standard deviation of that residual that we got. So we create our residuals like right here, and in order to know the standard deviation, we will find S. So basically that's the difference between these two. But anyway, that's everything for step 3. Now we're moving on to step 4, which is the conclusion part. Since P is equal to 0.0142, which is greater than alpha equal to 0.01, I know in this case the question didn't specifically set the alpha, which alpha level we should use. If the question didn't say specifically in a test, you would just assume that will be 0.05. But in this case, we chose 0.01 just for fun. We failed to reject null hypothesis, meaning we cannot say that there is a linear relationship between frying time and predicted. That's a key word. Don't forget to say in your conclusion. Because we're using LSRL, remember from Unit 2, whenever we are dealing with that type of graph, we always have to use this keyword, predicted. Predicted, predicted, predicted. Repeat it for yourself 3 times. And predicted moisture content, but the residuals showed a pattern, meaning a nonlinear regression might be better, and the residuals were skewed. So remember in step 2, when we are testing our conditions for residual plot and residual box plot, we found out that there is a pattern for residual plot and the box plot is skewed right. So T-model is questionable. That's where we call back. We restate that possible source of error in our conclusion. I mean, it's not source of error, it's just maybe a linear model isn't work that good. So maybe we will choose another model in some cases if the question asks us to do so. So that's just showing a more full picture. Okay, so moving on to this question. This is a computer printout question. The question is saying, what is the relationship between the amount of TV watching and cholesterol level in kids? A sample of 100 children was observed, and the results are shown in the table below. Construct a 99% confidence interval for the slope of the regression line. So look at all of those data. You might be shocked at the beginning or overwhelmed. And don't worry at all, because I was at the first time too. So we first need to recollect or rearrange those data a little bit. Otherwise, we will just lost in those chunk of data. So what data are we really using or really useful to us? Well, first of all, we know that this is a LSRL, meaning this is a linear model, meaning the format for this will be y equal to mx plus b. Therefore, we will definitely use our SS. That's definitely useful. That's model and residual. Degrees of freedom and MS, not really sure what that is, but we'll see. We'll leave it just as neutral. But for the lines that I cross out, we don't even need to care about it at the beginning. For the rest of them, we will pick as we go through the questions, which one is useful to us, which one is not. And most important informations are actually lying in the bottom. Time and constant. So actually it's cholesterol. So what's our y and what's our x? Well, we want to find the cholesterol levels in kids, meaning that will be our y, or y hat, more accurate. And we want to find the time of watching TV. So that will be our x. And you can see coefficient, this will be b, and this is constant, so this will be a. Standard error, meaning this will be SE sub B, and T will be here. And we know that this is a 95% confidence interval, the data right here, but the question is saying a 99% confidence interval. So will this be wider than 95% confidence interval or narrower? I believe you said wider. Yep, because it covers a larger range of data. So just as always, starting our first step, which is saying what's beta meaning. Beta is the true slope of LSRL between TV time and cholesterol level in kids. So remember to say the true and slope. Those are the two keywords. And LSRL. Second step is, first of all, naming the procedure. What are we doing? We're creating a 99% T interval for slope of LSRL. And because we didn't provide it with raw data, meaning we cannot enter those data into our calculator and get the residual plot and residual box plot, therefore, all we can do is assuming. Assuming the residual plot has an equal number of positive or negative residuals, there's no fan shape and no pattern. And assuming the residual box plot has no skewness or outliers. And that's all you want to write for step 2. Moving on to step 3. Remember the formula we're using to calculate the z interval and t interval. For z interval, it will be x bar plus or minus z star times standard error. For t's interval will be b plus or minus t star times se sub b. So it's like rearranged a little bit, or the format is exactly the same, but it's just the letters shifted a little bit. So all you want to do is plug in the values from our computer printout. What's our b? Well, b is our 0.044. And plus or minus, what's our t star? Well, that one we need to get from our calculator. It's not that hard because we already know that we want to create a 99% confidence interval, meaning you will first use 1 minus 0.99 gives you 0.01. Using 0.01 divided by 2 gives you 0.005, I believe so. You will go into your calculator doing inverse t and hit enter that number into that, and you will get the numbers right here. So that will be 2.63, I believe. Sorry for the bad handwriting. What's SE sub b? Well, it's already in the computer printout. It will be 0.0105. And enter that into your calculator too, and you will get a confidence interval like this. It's also not a bad idea to rewrite the equation. Gives you y hat equal to negative 2.135 plus 0.044x. This is our LSRL original equation from the data, or from the computer printouts that given to us. And the degrees of freedom will be 98. It's also listed into our computer printout. So you can see the pattern right here. Whenever the question gives you a bunch of informations, you don't need all of them. Most of the cases you don't. Maybe you would just need 10% of them, mostly. So what you want to do is really pay close attention to the data that given to us. Make sure to use the data from the table and to use them as effective as you can. And then that's all for step 3. Moving on to step 4. Draw the conclusion. I am 99% confident that for every additional minute in TV time, the predicted cholesterol level will increase between 0.96 and 0.072 point. This will be 0.016 and 0.072 point. Sorry. So you can see I can't even read my handwriting. So this predicted is also a keyword that you want to draw, just as our last question. When you are doing a confidence interval, you also want to use predicted, since we are using LSRL, right? Every question related to that, use predicted as your keyword. Okay, so I'm not really sure what you think about these two questions, but in my opinion, I like the second one better, because I always feel like confidence interval are way more easier than test. So I don't know if you're feeling the same thing for me, but it's okay if you don't. Leave your comments below if you want to share your thoughts or any questions. I will make sure I can answer them as soon as possible. But enjoy the video, and thank you so much for watching.